Welcome and thanks for tuning in. In this presentation, I will talk about defining a novel transportation distance on graphs and manifolds and its application to hypothesis testing of distribution collections. This is joint work with Raif Rustamov and myself. Many modern machine learning applications involve distributional data defined on non-Euclidean domains, such as manifolds and graphs. Example domains include simple manifolds such as circle, sphere, torus, and graphs such as social and spatial networks and brain connectomics graphs. Diving a little deeper, consider the distribution of per minute heart rates collected from your Fitbit. Since the time dimension has 24-hourly periodicity and the intensity dimension is linear, the underlying data domain is a cylinder. Given a collection of health monitoring data from a set of individuals, one can conduct tests to determine if there are statistically significant differences between behavioral patterns of different segments, such as males versus females or different age groups. The general hypothesis testing problem we deal with in this work is how to compare two collections of probability distributions. Although similar to two-sample testing, this is a higher order notion in the sense that our samples μi and νi themselves are distributions. Additionally, there are two variability sources in this problem, coming from estimating the distribution histograms and variations between individuals. Binwise treatment of histograms is not effective as it leads to increased variability when distributions shift along the domain, leading eventually to less powerful methods. Transportation-based distances are effective at handling horizontal distribution shifts. These distance measures, such as Wasserstein metrics, have gained popularity for capturing proximity of probability distributions on the real line. However, using them on manifold domains can be too expensive, both due to the distance computation and the use of resampling in the test itself. Sliced Wasserstein distance provides an efficient distance measure on Euclidean domains. However, it is not based on intrinsic constructs, nor does it capture graph domains. One of the main contributions of our work is the definition of intrinsic sliced Wasserstein distance. We propose to calculate Wasserstein distances between push-forwards of two distributions onto the real line, where the push-forward functions come from eigenfunctions of the Laplace-Beltrami operator of the manifold. The sliced distance is obtained as the weighted sum of those squared Wasserstein distances. Our proposed distance is able to utilize the intrinsic geometry of the manifold, has many favorable theoretical properties, and most importantly, is amenable for fast calculation through finite dimensional approximations. Closed form expressions of eigenvalues and eigenfunctions for simple manifolds such as square, circle, sphere are available, and the graph Laplacians can be used in the general case. Either histogram bins or raw observations can be used to construct our hypothesis tests. The finite dimensional approximation comes from the choice of the number of slices or push forwards, as well as the number of quantiles used for Wasserstein distance calculation. We use two approaches of hypothesis testing, one using a two-sample U-statistic and bootstrap null, and the other by combining p-values from coordinate-wise tests. Moving on to the results, we look at power curves for tests at 95% confidence levels. Here the x-axis delta quantifies the discrepancy between the two data generating meta distributions. A good test should maintain rejection rates close to 0.05 for delta equal to 0 and quickly increase to 1 as the discrepancy delta grows higher. Our method performs favorably compared to a number of recent methods for simulated data on real interval domains, as well as the case where slicing is not done. We also did simulations for domains such as circles and cylinders with favorable results. On the enhanced activity monitoring data, we are able to detect differences between activity levels of individuals of almost all age group pairs. We also run a control experiment where the two comparison groups are randomly permuted to generate a null case. No statistically significant differences are observed for these null cases. Finally, we present an application of our method to the Chicago crime dataset. The unit of observation is the distribution of the type of crime, such as theft, across different geographic areas in Chicago over one day. Using our method, we observe weekday versus weekend differences, namely in Tuesday versus Saturday distributions for 6 types of crimes. No statistically significant differences are detected for Tuesday versus Thursday comparison, which was included as a control or null case since both are weekdays. This brings me to the end of our presentation. Thank you for your time and attention. Our sample code is publicly available on GitHub.